I'm your host, Eric Geisels. I'm a professor of economics at UNC Chapel Hill and a professor of finance at the Kenan-Flagler Business School. I have the pleasure of introducing today's speaker, Daniel Egger. Daniel is a member of the Quantum Technologies group at IBM Research in Zurich. And his research interests range from control of quantum, in particular, practical applications of quantum algorithms in finance. The paper he's going to present today is actually, one of the co-authors is Stefan Werner, who was our inaugural speaker for this webinar series. He will talk about warm starting quantum optimization, which is a really cool topic, no pun intended. For some housekeeping, please, if you have questions, write them in the Q&A tab at the bottom of your screen. And after Daniel's presentation, we will field some of those questions to him to conclude the webinar. So Daniel, it's all yours. Please share your screen, and I'm looking forward to your talk.
Hello, everybody. Thank you, Eric, for the kind introduction. So let me go ahead and share my slides. Very good. So I take it everybody can see this slide. Okay. So what I want to do today is to talk about warm starting quantum optimization. And I'll be presenting results which have been made available through the archive here on this paper. So everybody can go ahead and access this if they want to give it a read. So without further ado, let's go ahead and dive into the topic of interest. So what I will be concerning myself with here in this presentation is how to tackle combinatorial optimization problems with a quantum computer. Now, when you look at combinatorial optimization problems, the canonical example which comes to mind is the quadratic unconstrained binary optimization problem, the Kubo problem. And this is depicted in this equation here, where we have a set of n decision variables that can take on binary values, either 0 or 1. And then you have a quadratic term here and a linear term. And what we want to do is we want to minimize this objective function. Now, when you look at this from the point of view of a quantum computer, the procedure to map this to the quantum computer is the following. The first thing that we do is we substitute our binary variables to the Zi variables, which have values which are either -1 or +1. And what this then allows you to do is that it allows you to take the cost function and replace every Zi by a spin operator, right? So this means that you can then represent this in terms of a Hamiltonian, more specifically an Ising Hamiltonian. So if I take this cost function here that I have, and I apply this mapping from x to zi, and then I replace the zi's with spin operators, you would arrive at the following Ising Hamiltonian, which describes this optimization problem. And the nice property of this Hamiltonian is that its ground state, meaning the lowest lying energy level, corresponds in fact to the solution of our optimization problem. Meaning if I want to minimize this equation here, then I simply need to find the state which minimizes the energy of the Hamiltonian. And so you can take a little bit of a look at the small example that we have here. So if I take an example of a Kubo with two decision variables, namely x0 and x1, in this case you have x0 squared plus x1 squared minus the half of x0 plus x1. There are 4 different possible solutions here. The one that minimizes this is this one. And then finally, when you map this to an Ising Hamiltonian, you will arrive at a Hamiltonian, which is a matrix, and it is 4 by 4, and diagonal with the energy of each state shown here. So you can see that the lowest lying state here has an energy of 0. Then we have 1/2, two solutions with the energy 1/2, and then the worst solution here has an energy of 1. And then you can see here in this row that these different energies correspond to different states. So in this case here, when both decision variables have the value 0, as indicated here, you have the quantum state 0, 0, which has the lowest lying energy. Right. So one algorithm that we have to tackle these optimization problems with a quantum computer is the quantum approximate optimization algorithm. And the way that this proceeds is the following. We construct a state labeled psi of beta and gamma, which has parameters, beta and gamma, and we want to find the values of the parameters which minimize the energy. And the state here is parameterized in the following way. So we start off with an equal superposition state, and then we will be applying p layers, where each layer is made up of a time evolution here, which corresponds to the cost function, Hamiltonian, and gamma I is a parameter that we want to optimize. And then the second step in each layer is the mixer operator here with a parameter which is beta I. Now, you can kind of see a depiction of this quantum algorithm here with 5 decision variables here, where each decision variable is mapped to a qubit. The first set of Hadamard gates here implements this equal superposition state, meaning that we have all possible solutions loaded into the quantum computer, so to speak. And then the next term here, and here on the second row, this is the cost function Hamiltonian. And finally here we have the mixer operator, which is applied with the parameter beta. So this here would be a depth 1 QAOA. Now, the reason why this is believed to be a good algorithm to tackle combinatorial optimization is because it has some certain guarantees which it derives from the adiabatic theorem. So the adiabatic theorem implies that if you start off in the ground state of one Hamiltonian, and then you progressively and slowly deform this Hamiltonian into another one, then you will, at all times of the evolution, remain in the ground state if you are slow enough. So what we see here with this QAOA is that the initial state here, this equal superposition state, corresponds to the ground state of the mixer Hamiltonian, which is defined as the sum of the sigma x operators. And given that we have all possible states which are represented in the quantum computer, we have here an overlap with the optimal solution. And so by the adiabatic theorem, if we have a sufficiently deep QAOA, we are kind of guaranteed to stay in the ground state. And this is covered here in this paper by Fari. Now, it turns out that classical algorithms to solve combinatorial optimization problems are in fact quite efficient. And what they do in order to arrive at such efficiency is to leverage continuous relaxations. So here, when we look at the quadratic unconstrained binary optimization problem, you can in fact relax this problem to a simpler variant of the problem. Namely, if I relax the decision variables from binary to continuous, meaning that now x can be any value ranging from 0 to 1, then I all of a sudden have a problem which is a lot easier to solve. And you can kind of see what happens to this here in the two graphs that we have. So at the top here, we're showing the combinatorial problem that we had before with 2 decision variables. And then here, we're showing the relaxation of this problem when the decision variables are continuous here, right? So x1 and x0 range from 0 to 1. So the idea here behind warm starting quantum optimization is in fact to leverage such relaxations in order to warm start quantum algorithms. So what we will do here is we will suppose that we have a cubo, and we will first relax the problem and find the continuous solution to this relaxation. So now we obtain a solution, C star, which is continuous within the range of 0 and 1. And we can find this efficiently using classical computers. And we will use this relaxation to warm start QAOA. So what we first need to do is we need to prepare an initial state here, which corresponds to the continuous relaxation of the problem. And you can do this by using Y rotation. So you can see here that we have replaced the Hadamard gates with Y rotations. And the amount of rotation that you do on the Bloch sphere will depend on the value obtained from the relaxation, namely the C star sub I. And this then prepares an initial state, which is shown here. And you can see now that the probability of measuring 1 in each qubit is given by C star sub I, right? So simply taking the square of this quantum amplitude. Now, we have changed the initial state here, which means that we also need to change the mixer operator, because we need to ensure that the initial state is in fact the ground state of the mixer Hamiltonian. And so the mixer Hamiltonian is no longer the X operator, but is this modified Hamiltonian here for 1 qubit. And so then the overall mixer used here in the Warm-Start QAOA is given by the sum of these Hamiltonians. And we can in fact implement this time evolution in the following manner. So you can see here now that instead of having an X rotation by an angle beta, what I in fact have is a rotation around the Z-axis with an angle of -2 beta, which is sandwiched between these RY rotations given by the angle theta I. And here, once again, the angle theta I is given by the solution to the continuous relaxation of the problem. So when you look at the quantum circuit that we are dealing with, you can see now that we have replaced the mixer operator with a few more single qubit rotations. So this is the algorithm that we will be running. You can see here that this is a depth 1, but nothing prevents you from increasing the depth of the warm-started algorithm, right? So you can add several layers of cost function Hamiltonian followed by mixer operators. And once again, we want to optimize the parameters beta and gamma. So this is warm-started QAOA. Now, there is one thing to keep in mind is that there is a little bit of a snag that we need to address here. Let's suppose that the solution to the continuous relaxation is either 0, is not a 0 and not a 1. In this case, you have an initial state which is guaranteed to overlap with the optimal solution and is the ground state of the mixer Hamiltonian, meaning that you can apply the adiabatic theorem and then you are guaranteed to converge to the optimal solution as p goes to infinity, where p here is the depth of the QAOA algorithm, of the warm-started QAOA algorithm. However, if the solution to the continuous relaxation is either 0 or 1, then in that case, the warm-started QAOA will not be able to change the state of the qubit. And the reason for this is simply due to the nature and the structure of the gates that we are applying. So the cost function Hamiltonian only applies Z gates, which do not change the amplitudes of the states. So this means that in this case, we are not necessarily guaranteed to be able to deviate, let's say, from the initial state if it is either 0 or 1. So what you can do then is you can overcome this limitation by applying a small regularization. And this is referred to the parameter epsilon. So what we can do is we can project C star I to the interval ranging from epsilon to 1 minus epsilon, where epsilon here is a small quantity, which is larger than 0. And this is depicted here in this graph. So you can see that I have two decision variables, x0 and x1. And the Cases that are a bit sensitive is when either of these decision variables is 0 or 1. And this is depicted by the square, the blue square here. So then once you apply this small regularization, you will then be dealing with any solutions here or any initial states, which is contained within the green box here. And it's also interesting to note here that when epsilon is equal to 0.5, meaning you start with the equal superposition state, you in fact recover the standard traditional QAOA algorithm as indicated by this teal dot here at the center of the graph. So in the paper that I am discussing, we presented quite a lot of variants to we proposed a sort of a framework in order to warm start these quantum algorithms. And this is going to lead to plenty of further directions to perform research, because there are several questions that you can ask yourself. So the first one is, what to round? And in this talk, I will be showing the case of the quadratic programming relaxation, which we just discussed. And later on, I will also be discussing semi-definite programming relaxations in the context of MAXCUT, and I'll show how that works out. But there's also different ways to, there's also different methodologies to look at this. Then the second question that you can ask yourself is, when do you do the rounding? And here there's a few options to do that. The first is that you can do rounding in the classical pre-processing, and I'll show an example of this in the context of MAXCUT. And the other variant is to do the rounding within the quantum circuit. So maybe let me elaborate on this point just a little bit. So when you prepare a quantum state, let's say we prepare a superposition of 0 and 1, and when you measure this state, you are in fact going to force the wave function to collapse into either 0 or 1. And this can be viewed as a form of randomized rounding. And so here, in this case, the rounding is done at the end of the quantum circuit in the measurement step. And then you can also ask yourself the question, how do you do the rounding? So in the case where you do the classical pre-processing, we'll show in the context of MAXCUT and Goemans-Williamson that you can use hyperplane randomized rounding. So with this, let me start to discuss one example here. And I'll illustrate this within the context of portfolio optimization. So when you look at Markovit's portfolio optimization, you are dealing with an optimization which typically looks like the following here. So what we want to do is we want to maximize a return of our portfolio, where mu is the vector of expected returns, and we also want to minimize the risk of the portfolio. And here, the risk is measured by the covariance matrix of the assets. And then you have a parameter Q, which allows you to control the trade-off between risk and return. And typically, you will also have constraints on this, like the following, meaning that you want to exhaust your budget. Now, typically, this problem is easy to solve when you are dealing with continuous weights, right? So here we have our decision variables, which are continuous. However, it becomes a lot harder when you are looking at some specific instances of the problem, where, for instance, you can only trade assets in odd lots, and then you start to have a problem with decision variables, which become binary or perhaps integer in some cases. And then on top of this, you may also add constraints that are binary. For instance, you could say that you want to invest in a fixed number of assets, and then the weights of all others would be 0. And this then can be modeled, for instance, through constraints and variables such as these, where the value of Zi is either 0 or 1. So when you are dealing with these mixed binary optimization problems, it can become quite tricky to optimize, even when your weights are continuous. Now, I'm going to use the context of portfolio optimization to first illustrate some applications of the warm start algorithm. And so we're simply going to assume here that we have a binary decision problem which corresponds to, let's say, selecting an asset or not selecting an asset. And you can kind of view this as, for instance, if I wanted to construct a portfolio in which all the weights are equal, so a 1/n portfolio, but I want to select only a subset of the assets in my investment universe. So to follow the warm-started methodology, what we will be doing here is we will first solve the relaxed version of the problem where the weights are continuous. And this will give us a variable C star, which we can use to warm start quantum optimization. And then we will use warm-started QAOA with the C star, and we will also compare it to a brute force search in order to get the optimal value of the problem. Like that, we can compare really how well our optimization is doing. And you will see here that the size of the problems that we will be considering are in fact pretty small here. And the aim is not necessarily to demonstrate any form of advantage here, but just to demonstrate that this warm-started QAOA is indeed giving us an advantage over standard traditional QAOA. And so we kind of want to study the convergence of this as a function of the QAOA depth P, and we also want to see what type of improvements the warm-started QAOA gives us. So portfolio optimization can kind of be represented as a graph here, and we will be dealing with dense graphs, of course, simply because we have a correlation between each of the different assets. And the problems that we will be dealing with here are very small, right? So it's 6 assets. This is in fact quite trivial to deal with a classical computer, but it's a very nice test setup for us to test our algorithms. And then we'll be implying a budget constraint of b equals to 3. Namely, what I want to do is just select the 3 assets which are best for my portfolio out of an investment universe of 6. And in order to do the benchmarking, we will solve first the C star, which is an easy to solve problem, right? Because the weights are continuous. And in this case here, because the problem is so small, I can also solve on a classical computer the D star, right? So this tells me whether or not later on my quantum algorithm will have found the optimal solution to the binary problem. So you can see here the difference in solutions of the discrete version of the problem and the continuous version for one instance of the problem. And you can see here that in the discrete case, we select assets 0, 2, and 5. But in the continuous version of the problem, we have a bit of weight here, for instance, which is put on decision variable number 1. But it's interesting to note here that the continuous solution to the problem is quite close to the discrete solution. So the warm-started algorithm will in fact be leveraging the proximity of this continuous solution to the discrete one. So let's take a look at this. What I'm showing here is some simulations of warm-started QAOA compared to standard QAOA for one instance of the problem with 6 assets and the budget of b equals to 3. And in orange here, you have the standard QAOA, which starts off from the equal superposition. And what we're plotting on the top graph here is the probability to sample the optimal solution. And you can see here that the warm-started QAOA in fact performs a lot better. So the probability of sampling the optimal solution for the warm-started QAOA is a lot higher. Now, on the bottom graph, we are plotting the energy that the system is finding. So the closer we are to this dashed line, which corresponds to the optimal solution, the better our algorithm is doing. And we see the typical behavior of QAOA is that as you increase the depth, the energy generally decreases. And you can see that for sort of these depths of P from 3 and above, you have an energy which is quite close to the optimal solution. But this doesn't necessarily guarantee that you do in fact find the optimal solution. And the reason for this is because we have enforced our budget constraint using these large penalty terms here, right? With with a factor of lambda, which is quite large. So what standard QAOA is doing here is it's managing to satisfy the budget constraint, but that doesn't necessarily give it a high probability of finding the optimal solution. However, because the warm-started QAOA is initialized with the relaxation of the problem, you can see that already at low depths, the probability of sampling the optimal solution is a lot higher. And then as you increase the depth of the QAOA here, the energy also decreases as you would expect, simply due to the adiabatic theorem. Now, here, maybe just to give you a little bit more information, the shaded areas on the plot, these correspond to different runs of the optimization started from different initial values of beta and gamma. So it shows that you do have some probability of converging or getting trapped in local minima. And this is generally a feature of QAOA landscapes, is that they tend to have lots of local optima. So they can be a little bit tricky to navigate for the classical optimizer. And furthermore, in order to test a little bit our hypothesis behind the warm-started QAOA, what we did is an extra experiment shown by the lines in blue here. And what we did in this case is we initialized the quantum circuit with a state which corresponds to the relaxation of the combinatorial optimization problem, but we did not replace the mixer, meaning we used the standard mixer from standard QAOA. And just as we expect, you can see that when you do this, this doesn't really manage to reduce the energy, and it kind of presents a bit of an erratic behavior here when you look at the probability to sample the optimal solution. So this really shows that when you design this warm-started quantum approximate optimization algorithm, you need to have both the right initial state and the mixer which corresponds to it. So in the graph that I'm showing here, we presented one instance of a portfolio optimization, but what we also did is we looked at many random instances here, always of size 6. And what we saw is that when you look at standard QAOA, here indicated by this cold start, it always tends to saturate at about a limit of 0.75 when you look at a depth p equals to 1. However, when you use the warm-started QAOA, you can see that you arrive at a much better approximation, as shown here. So what you're looking at on the x-axis here is the energy of the QAOA normalized to the optimal energy, meaning that of the optimal solution to the problem. So if you have a value of 1 here in this histogram, this means that for that particular instance of the problem, the warm start has found the ground state of the problem. And so what this histogram is showing you is that warm start in general improves over the results of standard QAOA. And this is also very nice in the area of quantum processes which have noise in it, because it shows that with a lower depth and therefore fewer quantum resources, you can arrive at a solution with a better quality using warm start. Now, this also has benefits when we look at it from the point of view of quantum annealing. And this is what I want to show in this slide here. So let me maybe guide you a little bit through the results. So the first thing maybe to mention is that QAOA is inspired from a trotterization of adiabatic quantum computing. So adiabatic quantum computing is a continuous process, and then you can go sort of time slice this time evolution into discretized time bits, which corresponds to a trotterization of the evolution. So what we're showing here is that a warm start speeds up annealing. And this is shown in the following case. So we have here some simulations. On the x-axis, we have the total anneal time. So the longer the annealing schedule is, the slower the whole evolution of the dynamics is, and the higher the probability is that you have to stay in the ground state throughout the annealing. So slower generally means a higher quality solution. Now, the number of time steps here simply corresponds to the number of steps that I have when I discretized this time evolution. So what we want to do is we kind of want to be able to find the ground state with the least resources possible, meaning a small number of time steps and a small annealing time. And the figure in A here corresponds to the case with a warm start, and the figure in B here corresponds to the standard QAOA, where we start off with an equal superposition state. And what you can see here is that the quality of the solution for the warm start is a lot better, simply judged by the fact that the energy here is lower for the same given amount of resources. And it's instructive to look at the time evolution of the states, and this is shown here in the bottom graph. So let me take you through this graph. So the dashed orange line here corresponds to the annealing schedule indicated by the triangle up here, the orange triangle. So that is the standard QAOA. And then the solid green line here corresponds to an annealing schedule indicated by the green triangle here for the case of a warm start. So you'll notice here that both annealing schedules have the same duration and number of time steps. So we can kind of compare their time evolution one-to-one. And what you will see here first off is that the initial state of the standard QAOA is not as good, simply indicated by the fact that it has a higher energy, meaning that it is further away from the optimal solution. And moreover, when you run this annealing schedule here, the standard QAOA, so with the standard mixer, doesn't converge to as nice of a value. And furthermore, you can see here that you start to get oscillations in the dynamics, which means that you sort of transition out of the ground state of your Hamiltonian. By contrary, you can see that the warm started mixer in this annealing schedule performs a lot better. And you can see that you arrive at a lower value for the energy of the system, which kind of indicates that you are being a lot more adiabatic for the same annealing schedule. So this also sort of makes sense, right? Because you're starting with a solution which is a lot closer to the optimal solution. Now, with this, I want to sort of change gears a little bit and discuss a warm start within the context of MAXCUT. So what I'll do first is discuss a little bit, I'll present the MAXCUT problem and then show how we can leverage relaxations of this problem in order to warm start recursive QAOA for MAXCUT. So the idea behind MAXCUT is the following. We have a graph which is described by a set of vertices. Here we have five vertices, so 0, 1, 2, 3, and 4. And we have a set of edges which shows how the vertices are connected. And then the task in MAXCUT is to find a partitioning of the graph such that we maximize the value of the cut through the edges. So for this particular graph, one instance of a MAXCUT is shown by this blue line here. So in this case, nodes 0, 2, and 4 are on one side of the cut, and nodes 1 and 3 are on the other side of the cut, meaning that nodes 1 and 3 are assigned the value of 1, and nodes 0, 2, and 4 are assigned the value of -1. And this is an example of a MAXCUT here for this small graph. Now, in mathematical terms, this MAXCUT problem corresponds to the following optimization problem, which is also a QAO. So this is simply the task to maximize the sum over all of the edges in the graph, where we have the weight of the edge, omega ij, so this is the weight of the edge between node I and node j, times 1 minus our decision variables, which is zi times zj. So each node is given a decision variable, and it can be either -1 or 1. So if it is -1, we have a node on one side of the cut, and if it is 1, the node is then on the other side of the cut. And this problem, this MAXCUT problem, is in fact NP-hard. If you want to find the maximum cut, it is an NP-hard problem and therefore very difficult for computers to solve. Now, fortunately for us in classical computing, we have very good relaxations for this problem that we can leverage. And one algorithm for this is the celebrated Goemans-Williamson randomized rounding algorithm. And what this does is it allows you to produce cuts using a classical computer, which have a size of about 88% the size of the maximum cut. And you can see that this is already quite good. It's a lot better than just simply randomly guessing on which side of the cut a node is. I'll show in the next slide a little bit how the Goemans-Williamson proceeds, but what it essentially does is it sort of computes a few vectors, and then it produces a random hyperplane, and this then allows you to determine on which side each node is on the cut. And just to do a little bit of benchmarking on this Goemans-Williamson, we decided to simulate it for different graphs. So each plot that I'm showing here corresponds to 100 graphs. And what I'm showing is the average of the size of the cut as a function of the number of cuts that we are generating with Goemans-Williamson. So here we have graphs which have 30 nodes. And in the top, we have graphs where the probability of having an edge is 50%. And at the bottom, we have fully connected graphs. So these graphs tend to be a lot harder to solve. And you can see here, as indicated by the green dashed dotted line, that for these fully connected graphs, the Goemans-Williamson only finds the max cut in about 60% of the graphs. But nevertheless, if you look at the average size of the cut which is produced, it's a little bit north of this 80%, which sort of is in line with our expectations of this algorithm. So maybe a few more details of how to use the Goemans-Williamson algorithm. So how it works. What we do is we take our MAXCUT problem, and then we do a semi-definite programming relaxation of the problem. Namely, we want to solve the following semi-definite program. And what this will do is that it will assign a vector on the unit sphere to each node in the graph. And once you have done that, you can generate a random hyperplane that passes through the origin of this unit sphere. And then all of the vectors which are on one side of the random hyperplane will be considered as being on one side of the cut, and all the vectors which are on the other side of the hyperplane will be on the other side of the cut. So for instance, here, if this problem here generated the vectors shown in this graph below, then the nodes 1 and 3 would be on one side of the cut, and nodes 0, 2, and 4 would be on the other side of the cut, generated by this random hyperplane indicated by the dashed line. And so the point of warm-started QAOA here will be to leverage this Goemans-Williamson algorithm in order to warm-start the quantum algorithm. Now, if you actually try out directly what I showed before, it in fact doesn't work out too well. And this is indicated by this graph here. So the first thing that we need to do is maybe let's take a look at and explain this graph here, right? So at a value of epsilon equals to 0, if I start this off with different Goemans-Williamson generated cuts, so each point in the graph here corresponds to one GW cut, you will see that at epsilon equals to 0, as discussed before, we're not able to change the initial state if it's only 0 or 1, meaning that these points up here simply correspond to the Goemans-Williamson cut, meaning that the warm-started QAOA is not really changing anything here. In fact, it's just the same as doing Goemans-Williamson. And as we increase the value of the regularization parameter, you can see that the quality of the solution gets worse and worse. So our warm-started QAOA here is not really doing too well in this setting. So what we needed to do in order to get this to work a little bit better is to modify the mixer. And what we did is we simply flipped the signs of the RY rotations in the mixer. And if you do that, and you do a depth 1 QAOA and calculate here the energy of the cuts that this warm-started QAOA produces with this modified mixer, you will see that when you arrive at a value of around 0.5, you in fact recover cuts which are quite good and possibly even better than the Goemans-Williamson as indicated by some of our simulations. So this shows here that with this modified mixer, we can do, in fact, a bit better. But there is also one thing that we are giving up here, is that by changing the mixer, the initial state is no longer the ground state of the mixer. So we are sacrificing our convergence guarantee here from adiabatic computing in the limit when p goes to infinity. However, as I just pointed out, this tends to perform a lot better. And here we can ask ourselves the question, why? Why does it perform better? What is actually so special about this value of 0.5 for epsilon, as indicated on this plot here? And you can understand this, in fact, quite simply. If you look at a special case where at depth 1, if you choose gamma equals to 0 and beta equals to pi half, and you calculate the evolution of this warm-started QAOA on the ground state, you will see that it manages to recover the Goemans-Williamson cut, right? So if xi is equal to 1, we have a quantum state with value 0, and if xi is equal to 0, we have a quantum state in 1, up to a phase, but that is a little bit irrelevant here. So what is interesting here is that at a value of epsilon equals to 0.25, we have a quantum algorithm which can recover the Goemans-Williamson cut, meaning that it inherits the performance guarantees of Goemans-Williamson, but by changing the values of gamma and beta, it is also capable of creating states which differ from Goemans-Williamson. So this is why this epsilon point of 0.25 is very very interesting. Now, in the numerical simulations that we did, we used the recursive QAOA to tackle these MAXCUT problems in a warm-started fashion. So what I'm going to do next is I'm first going to present the recursive QAOA algorithm as first presented by Sergei Bravi in this paper here. And then I will show how to modify this recursive QAOA algorithm to give it a warm start in order to inherit the performance guarantees from Goemans-Williamson. So standard recursive QAA proceeds in the following fashion. We have a graph, Gn, that we are given, and we want to find the MAXCUT for this. And what we first do is we do a QAOA, just a standard QAOA, to obtain a quantum state here, which should already have a pretty good energy when you compare it to the energy of the maximum cut. And then we compute the correlation matrix between all the different variables. And this correlator here is simply the expectation value of this state for the different Z operators, for the different spin variables. And then we choose the value of this correlation matrix which has the highest magnitude. So we pick out the two variables which are the most correlated, either positively or negatively. And then we replace one of these decision variables by the other one times the sign of this correlation matrix. And this then allows us to reduce the size of the graph by one node. And by doing this, we obtain a new graph here, g of n-1, that we can then use to reiterate this this process. And then by iterating through this, we will progressively reduce the size of the graph until it is small enough such that it can be tackled with, for instance, a classical solver. And then at the end, what this recursive QAOA will output is a list of replacements. And you can see an example here where what we are doing is we are replacing the first decision variable Z1 by the decision variable Z4, but with a sign difference of -1. And then what the next replacement here is showing is that the decision variable Z2 is the same as decision variable Z3, and they have the same sign. So this kind of shows you the type of output which the recursive QAOA produces. Now, we're going to modify this algorithm here in order to warm start it using a Goemans-Williamson pre-solver. So the recursive warm start QAOA algorithm functions in the following fashion. We have a Goemans-Williamson pre-solver, which for the given graph, G of n, is going to generate big N different cuts using the randomized rounding procedure that I described previously. And then out of these N cuts, we're just going to take the N best cuts. And the reason why we do this is just to reduce a little bit the number of QAOA instances that we are going to run. So then for each of these best cuts generated from Goemans-Williamson, we are going to run a warm-started QAOA with the modified mixes that I showed you in the previous slide. And then by optimizing the values beta and gamma, we are going to get a state here which ideally minimizes the energy of the Hamiltonian. And then for each of these cuts that we have run, we get one such state. So we need to have an aggregator which allows us to combine all of these different states together into one. And you can simply do this by summing the counts that you measure for the different bit strings that these QAOAs produce. Then from this aggregated counts dictionary, what we are going to do is going to compute the correlation matrix as we did in the previous slide. And so this then, once again, gives us an idea of how the different decision variables in a problem are correlated, and those that have the strongest either positive or negative correlation we will use in order to replace one with the other, right? So for instance here, if Mij is the largest magnitude in this correlation matrix, I will replace decision variable Zi by the sign of this Mij times decision variable Zj. And then this is something that will produce a new MAXCUT problem that I can once again send through this recursive warm.QAOA, use the Goemans-Williamson pre-solver, generate cuts, and so on and so forth. And once the problem size is reduced to sufficiently small instances, we can then tackle this with, for instance, classical optimizers. And so once again, what we're going to come out of this here is a list of replacements. So we tested this warm-started recursive QAOA algorithm on a few different instances of graphs. And I'm showing these results here. And what I will do now is just describe a little bit the different graph instances that we tested and what each graph here is showing. So we did this with 4 sets of graphs of different types, and each set of graphs contained 100 different graph instances. So the top row here corresponds to graphs with 20 nodes, and the bottom row corresponds to graphs with 30 nodes. The column on the left here corresponds to graphs in which each edge had a probability of appearing of 50%. And then the edge was given a random weight, which was either -1 or +1. And then the graphs here on the right, these correspond to dense graphs, meaning fully connected, more or less, with an edge weight which is in the set from -10 to +10. So there's a few things to say here. First off, the larger the graph, the harder the problem is to solve in general, right? So a 30 instance problem, an instance with 30 nodes is harder to solve than an instance with 20 nodes. And furthermore, the more edges that you have in your problem, the harder it will be to solve. So generally speaking, when you go from left to right, the problems get harder. And when you go from top to bottom, the problems get harder. And now we are showing the results here of 4 different solvers. So the first one here is simply a Goemans-Williamson solver, which was allowed to generate 10 cuts. And then for each graph, we take the best of these 10 cuts and accept that as the solution. So you can see here that for instance, for these graphs here, that this Goemans-Williamson managed to find the maximum cut in about 70% of the graphs that we tested. And this is shown by this blue bar. And you can see that as the graphs get larger and as they get denser, the magnitude of this blue bar starts to decrease. And you'll see that throughout all of the different solvers. Now, when you apply standard recursive QAOA, this is the data shown here in orange, and you can see that this already performs a little bit better than our Goemans-Williamson, which was only allowed 10 cuts. Then we have the warm-started recursive QAOA, which leverages the 5 best cuts that were generated out of the 10 cuts here. And you can see that this already does a lot better. This already does better than the standard recursive QAOA and the Goemans-Williamson. So kind of indicates that this is outperforming the other solvers. And then just to further benchmark this a little bit more, we compared our warm start recursive quantum approximate optimization algorithm to a recursive classical Goemans-Williamson algorithm. And this is shown by the distributions in black here. And what this algorithm does is it's kind of inspired from the recursive QAOA, where we have a Goemans-Williamson, which generates a cut, and then we calculate the correlation matrix based on several of these cuts, and then use that to eliminate one decision variable, and then reiterate with a new graph with one node less. So it's very similar to the standard recursive QAOA, except that it doesn't have the quantum part in it. And you can see here that this outperforms the standard RQAOA in the graphs that we tested, but it doesn't outperform the warm-started RQAOA. So our simulations here indicate that this warm-started RQAOA performs best of the 4 instances that we tested. And here I'm arriving at the end of my presentation, and I will quickly conclude. So what we did in this paper is to present a framework to warm start quantum optimization algorithms. And when you're interested in warm starting quantum optimization algorithms, there are sort of 3 key questions to ask yourself. So what should I round? When should I do the rounding? And how should I do the rounding? And if you look at the mathematical literature, there's lots of different ways to do each of these 3 steps here. And so what we did is we presented the warm-started QAOA and the warm-started recursive QAOA. So the first one does a QP relaxation, and the recursive QAOA can leverage SDP relaxations. And there would be, for instance, avenues of research to explore other types of relaxations and other methods of doing the rounding. We showed that this works well in simulation. So our recursive warm-started QAOA tends to outperform the other solvers that we tested, at least on the graph instances that we tried out. And it also lowers the circuit depth to get a given quality of solution, as I indicated with the solutions to the portfolio optimization, meaning that with a lower depth warm-started QAOA, you can kind of arrive at the same quality of solution for a QAOA, but that would require a much deeper quantum circuit. So this is kind of a very nice method, for instance, to lower the amount of quantum resources that are required on quantum computers. And this is also particularly important given that quantum computers today are noisy and that the gates that we use to implement these algorithms are imperfect. And with that, I would like to thank you for your attention.
Thank you, Daniel. This was quite a lot of nice work. Thanks, and also a very nice presentation. We have one question that pertains to the MAXCUT. And I think you can see the last one, right? You can see yourself, the Q&As. It's about, I think, the separating hyperplane in is it relative to the unit sphere, or is it a symmetric n by n matrix s to the s to the power n is the question. I think relates to that random hyperplane on the unit circle question.
Yes. Yeah. So the Goemans-Williamson is going to produce a vector for each node, and these vectors have a unit norm. And the hyperplane that we generate is simply a hyperplane which passes through the origin of the unit sphere. And you can kind of generate this random hyperplane by generating a random vector, and then there's a hyperplane associated to this. And by taking the dot product between the vectors of each node and the one of your random hyperplane, you will then have a quantity which either has a positive sign or a negative sign. And if the sign is positive, it's on one side of the cut, and if the sign is negative, it's on the the other.
I have some thoughts on this. And it relates to the portfolio optimization problem, which is the one that I'm the most familiar with. So the question I'm kind of thinking about is, do you always want to warm start? And would you have a criterion to decide whether that's the case? Let me explain. I think your simulation of the portfolio, I looked in the appendix, is a number of independent geometric Brownian motions. So the covariance matrix is kind of diagonal. And in that case, your optimization problem sort of is easy because you're going to go for the assets that have the lowest variance. And you look at the combination of that. And so you could sort of see that in your continuous solution. Your continuous solution is really picking the top 3 assets almost surely with the lowest variance. But there could be situations where you make this more challenging, namely where you would have either correlation structures that make this a little bit more challenging, or you could add transaction cost, and so that you're also kind of thinking that your continuous solution is not so trivial actually to solve. And so you could sort of then think, when am I going to, then you're going to have a trade-off between warm starting, solving that problem, and then solving the subsequent problem. So there is a speed versus accuracy kind of trade-off. Are you thinking about this? I mean, I understand that you want to present something where it always works very well, and it's impressive, and it makes a lot of sense. But I would also be thinking about the fact that particularly in the portfolio application, the one that I'm kind of more familiar with, you may not want to necessarily do that.
Yeah.
You might be misguided by your warm start.
Yeah, I think that is actually a very good question, and it makes a lot of sense to try this out on hard instances to see if we're not biasing ourselves too far away from the problem. And I kind of discussed that in the extreme case, if let's say you have variables which are the exact opposite of what you would like to what you would like to get for the binary case, then if you don't have this regularization parameter, you don't converge at all. So I think that for these difficult instances here, this might actually be a case where you want to try and scan a bit over the parameter epsilon, the regularization parameter.
Right.
So as you move towards epsilon equals 0.5, you go towards the standard QAOA. And in that case, you don't have a warm start anymore. So we really have a continuous parameter here that we can use in order to kind of control the amount of warm start that we want. And it's not something that we looked at in the paper, but I think that's an excellent suggestion of something to look at.
Yeah, makes sense. We're kind of running out of time, and I don't see any other questions. So let me just conclude by saying that we have our next webinar, which will be around middle of March. Sorry, the exact date hasn't been determined. It will be by Austin Gilliam from JP Morgan, who will be talking about some cool research that's going on at JP Morgan in quantum computing. For all of you out there, thank you for participating. It's a pleasure to have you. Daniel, you gave an absolutely wonderful presentation about an absolutely wonderful paper. Thank you very much, and talk to you later.